So hi everyone, welcome back after spring break. So we'll start with the basic discussion of Shell Lab and what you'll need to do for this. So this is basically our agenda. We're going to talk about what a process is and what signals are and why you'll need them in your Shell Lab, followed by basic introduction of what you need to do in Shell Lab. So starting off, what is a process? Now a process is basically an instance of program execution, and whenever you want to execute a program, you have different states associated with the process, like knowing what is the stack pointer, what is the instruction I'm executing, and what are the various states during the execution. Something like what is the process ID, process group ID, and so on that is associated with each process. So all these properties need to be maintained, and if you look at it, the kernel will ensure that all of these properties are maintained in the state and will allow you as a user a certain functionality that you can get these data. For example, you can read the process ID by using getPID. So things like these functionalities will be given by the kernel. And another important system call that is the fork. Now what is fork is basically when you're running a current process and you want to create a new process, you'll just execute the system called fork. Now what happens when you create fork is that within the kernel you'll create a new set of memory regions, new set of states that is to be required to hold the new process, and all of its state will be maintained in the new location. Now whenever you do this, the parent has to know if the process has been created or not. So that's why fork returns two values. One is a value of 0, which is to the child, for the newly created child, and another is the PID for the parent. Now what is this PID? The PID is the PID for the child it created. Why does the parent need to know this? Because parent needs to keep track of what child it created, and the best way for it to keep track is to get the PID. Since the PID is unique for each process, the parent will know, okay, once I have the PID, I have a unique identification for the child that I've created. So this is the unique ID that it will maintain. And in case the fork fails, it returns a -1. Now the biggest important thing that you will have to keep in mind is that after you do a fork, you cannot, as a user, we cannot really determine if the parent will run first or the child will run first. This is completely up to the kernel, and the kernel will decide whom to schedule first. Now the other important system call is execve. So execve is basically a case where you want to run a whole new set of program, and you'll use execve. Now what it requires is the file name and the arguments and the environment variables that are passed to it. Now the file name can be as such a path to the file that you want to execute. For example, if you're executing the ls command, this one will be /bin/ls. So this is basically passed as the file name, and you'll execute this. Now what this basically does, once you do execve, it basically tells the kernel that I'm no longer going to execute the current program I'm in, I'm going to execute the new program which is given by this path. So what the kernel will end up doing is, it'll replace the state it maintains in the kernel with the file, this particular file, and it'll maintain the state with respect to that. Now once execve is called, if it's successful, it'll never return to it. The reason it'll never return is because you're saying start executing a new program. Once you say execute a new program, there is no way it can come back to the old program because it doesn't know where it came from. So, but if there is a failure, it'll return a -1. And any system or anywhere that you want to execute a new process, the combination of fork and exec is what is used. Fork will create a new set of memory regions inside the kernel for it to maintain the state, and execve will ensure the exact program that you want to execute. It will allow you a chance as a user to execute those programs. And the other important system call is exit. Exit is basically saying that, okay, I've done with my job, now free up the location. So that is what the exit system call does, and once you do it, it will terminate the process that is being called, and once you do that, the process goes into a state known as zombie state. Now what does the zombie state mean? It's basically saying that the process has terminated, but the parent of this process needs to know that the child has exited and needs to take appropriate action. So what is an appropriate action there? The parent will say, read the exit status of the child. Now what is an exit status? Now generally a program starts with main, and in main you'll do something as say return 0. Now this 0 becomes the status which is then delivered to the parent, and the parent then reaps the child. Now what does reaping a child mean? The parent will ensure that I have no state information associated with this particular child maintained, because everything is used up and we no longer need it. So for this particular thing, the parent will ensure that it waits until it gets the information from the exiting child and it reaps it. Now during this operation, there are various possibilities. It's possible that the parent has exited before the child exits. Now what happens then? Now in that case, the exiting, the clearing of the zombie state will be done by the init process. Now init process is a process that is created right at the start of the kernel. So whenever a kernel launches, the first process it will create is called the init, and that will continue to run forever until you shut down the system. So any particular process that is trying to exit and we'll see if its parent is dead will be delivered, its state will be delivered to init, and init will ensure that it reaps the status of this particular child. So that's the exit system call. Now another important system call is waitpid, which you will be needing to understand in your shell lab. Now what does waitpid do? It takes in 3 arguments, which is the PID, status and options. The key thing to notice here is the PID. It basically says if you pass in a particular PID value there, this particular process will wait for the child who has the PID PID to basically terminate. And so the wait function allows the parent to know that this child has exited, and it will continue to wait for until this period. Now the key thing here is the PID must be the direct child of the invoking process, which means it should be its own child. And if the PID is -1, then it will wait for any child in the current process. It's possible for a process to do multiple forks, which means it can create multiple processes. And when you do wait PID -1, it is essentially saying that wait at least until one of the child terminates, and that's why you give a -1. And the return value here will be the PID of the child that it is trying to reap, and the options there are different possible options that are available. I mean, more details of this you can read the signals or read the textbook, which has all the details of different functionalities that are there, all of which is not exactly needed for us in the shell lab, but some of the key ones is W no hang, which keeps executing the caller until it terminates, and W continue, which will say, do I need to report all the children that are going to continue as well? So these are various options that are used. And set PGID. Set PGID is a system call which sets the process group ID. Now every process that's running has a process ID, which is a unique identifier, and a process group ID. Now process group ID will typically be the ID of the process whose parent. So if you have a main process here, say P1, and whose PID is say 1, or let's say 2, and PGID is say 3. Then whatever child it creates will ensure that it has the PGID same as the parent, which is 3. And this will keep happening. So the reason that this is there is so that to ensure that the child knows who its parent is, so that it can identify its parent easily. So this is the reason for having it. And this again has 2 parameters. First one is when PID is 0, and in this case the set PGID is applied to the calling process, which means it will get its new ID. And if PGID is 0, then the PGID is the PID of the process itself. So if a new process here is created and it has an ID of say 4, then if you pass in set PGID 0, 0, it will ensure that set PGID 4, 0, it will ensure that this will also get a value of 4, so that you can assign it a new process group ID. This is the basic diagram. So in this case, where here you'll see that this is the main parent process, which has a PID 5 and PGID 8, and the key thing to note here is this particular process can only reap these 2, and if this has to be reaped, it will either be reaped by this particular process or will be reaped by init, which is the main process that runs, and it cannot be reaped by this. So that's the key thing to understand. And something that is critical and important here is the concept of concurrency. because you don't really know if the parent executes first or the child executes first, you don't really know how the output of this will be. For example, here let's say once you've done fork, let's say the child is executing first, which means the child will say my PID is 0 and it will do child, and then it will exit. After this happens, then the parent might run and it will execute parent, and then it will return. So in this case, you'll see a child and a parent being printed. But what happens if the parent runs first? You'll see that the parent will print this and then the child will print this. So you'll basically have two possible outputs. So child parent or parent child. Now, one of the key things that you will have to keep in mind while doing your shell programming is to make sure that you take care of all these concurrencies. You basically want a very standard and pre-described output. You want it to run in a particular way. So you basically need to keep track of that. And how is this done? For example, we spoke of wait PID, where we said the wait PID will wait for the PID of the process that is passed as parameter until it basically terminates. So we, as a parent, this particular PID process knows the child PID, so it will wait for this until it is exiting. So once it exited, then it will continue. So this way you have avoided the concurrency issues and made sure there's only one possible outcome, where the child will execute first followed by the parent. So which is what is required. Now let's deal with signals. Now signals are a basic way of communication between processes. This is basically a communication between say a parent and a child and so on. And how this happens is there are different possible ways. One is control C, control V, and control Z and kill. Now control C is you would have possibly done it in, say, when you are running programs. For example, you use a while one loop, which means it will never terminate. Now one of the ways that you terminate a program is hit control C in your keyboard. So that's a way of sending a signal to that process saying that, okay, now you can stop execution. Now control C is basically the default operation for it is to terminate the process, and hence when you do control C, it will terminate the job. Now signals are basically asynchronous, which essentially means that there is no pre-described time or exact period when you're giving it the input. It's like you're saying, I'm giving you a control C or a control Z operation, but when that gets delivered to the process is highly dependent on the kernel. So the kernel will decide when to deliver it, and it's basically going to interrupt the execution of the current process and then deliver the signal. So, and there are also concept of queuing, which means if there's only one signal that is delivered at a time to a particular process. So if there's 100 child processes that are dying and all of them send a sick child, now the parent will just receive one sick child. This is the way that the kernel ensures that only one signal is delivered to the parent process to ensure that it is able to reap each of them one by one. Now the reason why it has to just deliver one is that it's possible, since the signals are basically asynchronous, it's possible that it can get delivered at different points in time. So you might say deliver the sick child of say the process with PID 4, then 5, then 6. Now it's possible that the kernel will see 5 first and it might deliver this to the process first, which means 4 will come later. So things like these can happen because the whole operation is asynchronous, and hence the kernel will ensure that once multiple things are happening at the same time, it will ensure there's just one delivery of the sick child, and with this one delivery, the handler that is there can ensure that it reaps all 100 of them, because it will know that all the 100 are terminating, because it will be able to find its exit status. And once it has its exit status, it's going to be able to reap them. So, and thus the kernel will ensure only one of them is delivered. Now, whenever a signal is basically delivered to a process, you can do 3 things. First is ignore the signal. Basically, the parent process says, I don't care what happens, I'm just ignoring this. This is one case. The other is the terminate the process, where the parent will just say, okay, terminate the process, I don't really care what is the status it has. So, and the last case is, you will catch the signal by executing a user level function, which is a signal handler. Yeah. Yeah, the idea of this is being, so whenever a process is trying to exit, it will set its exit status, right? So one way that the parent can know what, do I need to exit, I mean reap all of them, is to wait on the sick child. And the other way is inside the handler, it will keep waiting for the process to, the child to terminate and then start reaping them using wait bit. So with that, it will be able to reap all of them. And the idea of delivering just one, as I said, was the reason that you have multiple things being delivered. It couldn't go out of order, and it will ensure only one of them is delivered. So, and yeah, as I said, one of the three possible ways are there. So in your shell implementation, you'll be mainly doing the third one, where you'll be writing your own handler to ensure how the particular child is going to be reaped. Now, one other form of sending signals is using kill. Now, kill is basically you're going to say kill the process with ID that's passed as the first parameter and what is the signal you want to deliver. Now, the process ID can be one of two types. It can be a positive or a negative value. Now, a positive value indicates that kill a process with PID is equal to ID. That is the parameter you pass. And if it's negative, you're going to kill all the processes with the process group ID is equal to negative ID. Why it's negative ID? I'll show you with an example. So for example, here you're sending kill 8 and sig int. So you're basically saying kill the process with ID 8 and send it to sig int. So, and the process with ID 8 is here and it will deliver a sig int to it. So it will basically be interrupting the particular process. Now the next case is where you pass in a negative value. Here you're saying kill all the processes whose process group ID is 8. So if you notice, all of these process group ID is 8. So it's basically going to send the kill operation to all of them and send in the signal sig int. So that's basically the difference in kill. And in terms of handling signals, you basically have the signal function, so which takes the signal number and the handler. So you're saying, and this is basically for you to register if you want to have your own signal handler. The case 3 that we spoke about in terms of handling signals. Now what happens here is you're saying that this is the signal number and corresponding to the signal number, this is the handler that I want you to execute. So it's going to get registered with the kernel, and whenever the kernel ensures that this particular process gets a signal of signum type, it will directly call the handler that you've registered. And that's the overall operation. And sig handler is basically a function, a single function which takes in one argument and does not return anything. And the argument that it gets will be from the kernel. And when a signal is caught, now its default behavior is basically to ignore it. So, and once you register, it will ensure that this particular signal handler is called. Now, since all these signals are a state for a particular process, and as we spoke before, all the states are maintained by the kernel. So the kernel will ensure that it will appropriately call the correct handler corresponding to the signal. So there are some signals which by default cannot have a different handler. One of them is sig kill and the other is a sig stop. So you basically cannot do signal, sig kill and then pass in a handler. This will basically fail because as a system implementation, the kernel will never allow you to override sig kill or sig stop. This is basically saying that you cannot manipulate the normal operation of these two, and this is required so that whenever the kernel decides, it can send a sig kill or a sig stop. Now the important thing again, as we spoke of, is that signals are asynchronous, and since they are asynchronous, you don't know how it will exactly execute, and this will lead to a lot of concurrency issues. So as we spoke of, when will the parent run first or will the child run first, and different things and different possible cases are there. And how will you handle all of these cases? Like we saw the wait PID example, you can use blocking. Now we'll discuss what blocking is. Blocking is the case where you'll use a particular signal mask and say block these signals. Now how can you do that? There are various possible system calls that are available that will allow you to do this. Now when a signal is blocked, then it will basically be continued to be delivered, but even though it's delivered, no action will be taken because you're saying currently block the signal. Now, once it is unblocked, if there is any pending signal that it has received, it will take an appropriate action. Now, how will you ensure that you perform blocking or unblocking? This is using the SIG-proc mask. We'll deal with what SIG-proc mask does soon. And wait for signals is basically a process needs to wait for a particular signal to be received. And how will you wait for a signal? You can use a SIG suspend. Now, we'll deal with what SIG-proc mask is and what SIG suspend is now. So, SIG-proc mask is basically a format of this where you have an options and a set and an old set. So what this basically says is, what are the options? Options are basically saying that do you want me to block these signals, unblock these signals, etc. So you'll pass in these. And what is SIG set? SIG set is the set of signals for which you want to block. So you'll probably say SIG int and 6CHLD and so on. You can put it as in the set to say that block all of these signals or unblock these signals based on the options that you pass. So you could do something like this. So this is something like saying, so how will you populate this particular SIG structure will come up later. But basically what you're going to do is, you're going to call SIG-proc mask and basically tell it block the signals. What are those signals? Which are this, and this will be populated with say SIG int and SIG child and different other formats that you want, which we'll discuss later. How will you populate this? We'll come to that. And so that's basically saying you block all these signals, and once you are able to block these signals, you can ensure that there's a correct ordering of execution, and you'll avoid a lot of concurrency bugs that you've seen. Now, it's not just sufficient to block, you'll also need to unblock later on and take appropriate actions, which you'll need to figure out how that is done. And the other important concept is SIG suspend that we spoke of. So you're basically saying that currently suspend the execution of the current program until one of the masks in temp mask is received. For example, let's say you are the parent process and the parent process says SIG suspend and passes in a mask here. So what this mask could have SIG child. Let's say, for example, it just has SIG child. It's basically saying suspend the execution of this process until any child process delivers a SIG child. When will the SIG child will be delivered is when any of the child processes terminate, and when any of the child processes terminate, the kernel will ensure that it is delivered to the parent, and once it's delivered to the parent will check, okay, I'm in SIG suspend, one of the process has terminated now, so I'm allowed to execute. So this SIG suspend will be useful when you want to wait for your foreground operation to finish when you're in your shell implementation. So you can look at this in details. So once the SIG suspend returns, then it reverts the process signal mask to its old value, which means it will no longer be suspended. And then 6 set OPT, 6 set operations. So this is the key thing that you want to fill each of these signals. Say for example, the ones that you pass here. Now how you can fill them is using these. There are various set of functions. First is SIG empty set. So you can basically create a signal mask which is empty currently, and then start filling it by using say SIG add set. So you'll say SIG add set. And pass in the signal and say add SIG child. So this way you will fill you'll fill this particular signal with various signals that you want to add to it, and so you can use each of them, and sig del set will remove this particular signal number from this set if it's present, and each of them have their return value indicating success and failure. Details of this you can view the man page at this particular link, and this will again be useful for you to set up appropriate masks while you're using sig proc masks and sig suspend and so on. So there is again a race condition that we spoke of, because the ordering of the parent and child may be different, and if the parent process wants to add a particular job into the set of jobs and the child already terminates, all of these will be an issue. Now we look at one possible race condition that can happen. Now in your shell implementation, you basically need to add every job that is created into a particular job list. Now what will happen here, let's look. So if you look at it, you're first doing a fork, and if it's the child, you're doing an exec VE. Now the reason we're doing exec VE, we already spoke. Let's say you want to do /bin/ls. Now you want this to be the program that is executed, and this will be passed in exec VE to say execute this program. But once this program is executed, you basically want the parent to add this particular job in the job list. Now by the time you do an add job, let's say if the child is already exited, finished execution, exited, and it's removed, it's trying to do a remove job from the job list. Now this is a typical race condition where you have not even yet added the job into the job list, but already you're trying to remove it, which becomes a typical race condition. So the idea here is you need to block signals, and that's what is here. So what is the signals that you'll have to block is what you'll have to figure out. How do you ensure you block signals here appropriately to ensure that you first are able to add the job into the job list, and at a later point of time you should be able to remove the job from the job list. So this will ensure that you follow concurrency, but for you to do that, you'll need to ensure what signals are to be blocked and which you'll need to figure out. So a basic IO introduction. So one of the things that you'll need to do in your shell lab is to do IO redirection, which basically is to take care of this and this operation where your input and output comes from. So typically when you want to open up a file, you'll generally get a descriptor. Now this descriptor is basically an integer, but you can sort of look at it as a function pointer in a way, or rather as a pointer. Now every process starts with 3 typical descriptors: standard input, standard output, and standard error. Your standard input is nothing but the input that you give on the console, that's 0. Standard output is what you see it on the terminal, that is 1. And standard error, these are the cases where when there is an error encountered, it will put it in this particular descriptor. So typically all these 3 are created for every process, and the kernel will ensure that this happens. Now every process will have its own file descriptor table. So it will be, so if this is a process, it will have its own file descriptor table. Say the set of FDs, which could be say 0, 1, 2, so on, depending on what it creates. And along with that, you will have an open file table. This is the open file table, and then you have the vnode table. So all these 2 are maintained by the kernel, and whenever you create a file descriptor, it will be basically a pointer to one of the open files, and the open file will end up pointing to the vnode table. Now the vnode table is a structure that is maintained by the kernel and is specific to a different kind of file systems that the system is running on. So, and your interface will be only with the file descriptors, where open file descriptors, which will be created once you do an open. So with this in mind, you will need to understand what dup2 means and what it does. This will be essentially useful for you to handle the redirection cases. Now what dup2 basically does is it takes in 2 arguments, an old file descriptor and a new file descriptor. Now the new file descriptor then becomes a copy of the old file descriptor. So let's say we had a descriptor of this kind, and we did a dup2 for say a descriptor say 3. which now essentially means that 3 will also point to the same open file table and will end up pointing to the vnode table. Now what does an open file table contain? It will contain list of properties associated with the particular file that you're opening along with the file pointer index, which means when you're trying to read a file, you'll have your index of what position you're reading. So all of this will be maintained in your open file table. So with having 2 of the file descriptors pointing to the same open file, you can use either of them to read the file, but both of them will share the same file pointer, which means let's say you have a file like this and you have A, B, C, D, E, and if the 2 is reading first, it will probably read A and it will update the file pointer to point to B now. And if you're reading 1 byte from using the descriptor 3, you'll end up reading B because they share the same file pointer. And this is maintained in the open file table. So this is one key thing that you'll be using in your shell lab for this redirection. So it suggests you to go and look at the details of what dup and dup2 does. And this will be a critical thing. So a practice, for example, here is, let's say you have a file ab.txt which just contains A and B, and you do this operation, what will happen? So if we trace through this, so you're creating a file descriptor here. So let's take this itself as an example. So let's say it's with the ID 1. So let's say the first when it opens, the file descriptor say is 1, and you're doing a fork. Now once you've opened a file and you're doing a fork, the child will get the same descriptor as the parent. So the child will have its own file descriptor table. Again, it will end up pointing to the same open file table because this is what the kernel decides to do, and this is how it maintains it. And once you do this, you're trying to read one byte from this particular file into this particular character. Now what will happen, since you're doing fork and doing this, both the parent and child will continue to run here, which means you'll be doing this operation twice, once for the child and once for the parent. Now the order of execution, it depends, so it's not under our control, and you'll be reading this A and B. So what will essentially happen is, since both of them point to the same open file table and they have a single file pointer which indicates what is the current data it's reading. So if you have A, B, and let's say the parent runs first, if the parent runs first, he'll read A and he'll probably print A. Now once the child runs, he'll do a read, and once it does a read, it'll read from the current position of the file pointer. Now once A is read from the parent, it will increment the file pointer here, and once the child reads, since it's sharing the same open file table, it will end up reading the next character in the particular file, which is B, and hence you'll read B in case of child. Now this order could be reversed if the child reads first. If the child reads first, it will read A, and the parent might end up reading B. So the order of execution again is not, it's not standard, so which you'll also need to take care. Now what are the different other possibilities? What happens if you put the file descriptor after fork? Now the key point there is, once you put the file descriptor after fork, you're not sharing the same, you're not creating a copy of the parent's file descriptor table, so which means it'll create a new pointer to a new open file table, which means essentially both will not share the same file pointer. So that's the key thing to note here. So you put this int ft after fork, both the parent and child will not share the same open file table, and each will have its own, but they'll have the same link to vnode, but the file pointer will be different for each of them. And since the file pointer is different from each of them, you can end up reading both A, B in both of them. So that's the key difference. So a lot of these are not very intuitive and easy to understand, so I'd suggest go read through, if you can, read through this handout and read through the textbook to understand clearly what this is. So you'll see this IO concept in the chapter 10, where it deals with dup and dup2 and what happens when you create a fork using where they share the same file descriptor and so on. So it will be easy for you to understand once you have revise these concepts. And with respect to shell lab, now there's a lot of starter code for you, which will essentially handle all the parsing operations, the way you read the input, etc. You will need to be working on only few of those functions to ensure that you complete it, and use the reference shell for test your behavior. So if you don't really understand what is the kind of output that needs to be generated, there's a reference shell that is already provided to you. Just run it with that on any of the trace files or on inputs of your own to see how it behaves. So that could help you understand how it works. And the other is the use of sig suspend. So we spoke of sig suspend, where you're suspending an operation until a particular signal is received. So make sure you use sig suspend and not wait PID for the foreground jobs. And you should basically avoid any of the while ones or sleep operations to ensure that you maintain an order. And you need to ensure you use only sig suspend and wait. And the reason why, say, while one or sleep won't work is you can probably do a sleep, say, of 20 milliseconds or say 2 seconds, but if the parent still runs first, you'll just sleep for 2 seconds, and the parent might continue to running without the child being able to run at all. So your sleep operation will essentially become useless. So it's best for you to avoid sleep, because sleep does not tell the kernel run the child process. It just says make me sleep for some certain amount of time and then continue running. So it's best you avoid sleep and while, and try using sig suspend, because it will ensure you have a correct ordering there. And so sig ents and sig TSTP will be forwarded to the foreground jobs or the shell, and you'll need to know how the process groups will be used in this case, and how will you deliver the signals to all of the processes for this, all of the childs belonging to that process. And as we spoke of dup2, you'll need to use them for IO redirection, and basically be able to see where the failures can happen and how will you handle all the race conditions. And it's possible that the race conditions are not easily reproducible when you run using the trace files. So it's the concept that you need to understand and take care of it while coding. So that's basically the entire shell lab. So if you have any doubts, I'd be happy to answer. Okay, cool. Thank you.